Okay, now we have everybody here. So today I'm going to be talking about lightweight fault isolation, which is a new feature for in-process isolation that RFC has been approved. We're working on bringing into LLVM. And this is a capability for providing very efficient isolation in process of code that we're worried about memory safety. So third-party and first-party native code. Before I get started, I just want to give a shout out to the whole community of people that have helped make this happen. Probably most of all the Android team and all the folks who've worked on LFI there. They've done amazing work. Sharjeel for helping to shepherd the RFC, and colleagues at Texas and colleagues at Google and colleagues in the LLVM community who've given us really helpful feedback and kind of amazing code to work with. So thank you so much. So to start off, I think we everyone agrees now that memory safety is a big problem. It's a big challenge we're facing, and we need better tools to deal with this. And unfortunately today we have limited options for this. Stay close to the mic. One option, of course, is kind of the unsound mitigations that we've relied on, from stack cookies to CFI. And these are great because they work with existing code, right? Everybody lives in mitigation. If you can just flip on a compiler flag, they're like, yes, I'm in. The problem with these is they're often bypassed, and it's very hard to reason about the benefits, right? You kind of ask people to go through this, enable this or that thing in your system, and then they do, and then they get popped again, and they're like, but you just told me to do that thing, and it was going to be secure, and I don't really know what I got for that effort and for the performance I paid. The other challenge, right, so another possibility, right, is rewriting code in safe languages. I mean, this is great because it actually gives us sound security. We know what we're getting when we do something like this. But the downside is that there can be huge engineering costs associated with this. This is, you're building another system. You had this code that was already, maybe is battle tested. Now you have to go through that whole process again. And the other thing is that this doesn't always play nice with the open source community, right? Often there's groups of people out there who are doing their thing, with their stuff, and we want to be able to use their code and benefit from their code, and either not take over ownership or try to force them into a different way of doing things. So we would like both these properties. We'd like to have sound security, but we'd also like something that works with existing code. So one option, of course, is process-based sandboxing. And if you work at a large company where people are willing to pay you to do this, this is actually a viable thing. But if you kind of look at the larger world, there's not much of this. So process sandboxing, of course, it does provide us sound security, and it works with existing code, but it has a lot of downsides to it in terms of the performance costs, in terms of context switches, creation, overheads. And so this thing makes things difficult to scale, and people can go through kind of amazing contortions to put this into their system, which adds lots and lots of complexity, right? Keeping pools of processes around and all sorts of juggling associated with this. The other bad thing is, right, is you kind of end up with this kind of broken developer experience. All of a sudden now you've gone from having an application where perf works, GDB works, right? You know how to do your thing, to a distributed system, right? You had your way of doing concurrency, you had your way of architecting things, and they've just shoved a bunch of process in there, and you're like, dude, what happened to my architecture? So is there another option, right? Is there something else we can do? So I started looking at this back I don't know, I'm not going to do math. 6 or 7 years ago, we were talking with our colleagues at Mozilla, and they're like, we have this problem, right? We have these dozens of third-party libraries that we use in the Firefox renderer for parsing content, for decoding, for spell checking, for all these different things. And if they get popped, somebody owns the renderer. So if I send you an image to your Gmail, you open it up, I pop your renderer, now I've got your Gmail credentials. Now I've actually got your credentials for google.com, because that's how site isolation works. And so I can do all sorts of terrible things as you. And we're like, this is bad, how can we fix this? And so what we ended up doing is building sandboxing of these individual libraries using WebAssembly, which at the time was very cool and cutting edge. So I guess it's still kind of cool and cutting edge. And WebAssembly, it lets you get past a lot of these limitations you have with process sandboxing, right? So it gives you this nice model of isolation that you can reason about, input validation of those interfaces, but it does it in a way that where you get 1,000 times faster context switches, very, very fast startup time. I mean, you're thinking about basically isolation, but as a language construct, as a compiler construct, rather than as getting the OS into your business. So this has been deployed in Firefox since 2021 on lots of different platforms, lots of different users. So we know this approach is solid. So we did this work and we're like, this is amazing. Like, how can we get this out there to more people? And then we started, trying things and burning through undergrads and grad students. And what we found out is that WASM has many limitations, right? There's a lot of code out there that you would like to sandbox that WASM is not a good fit for because of a lot of the properties, that are kind of baked into its design. And this really limits your compatibility in terms of your ability to sandbox existing code, and also limits performance. And I've spent years in the WASM community, working on standards, working with folks. I have a lot of love for that world. And WASM is solving a very particular problem, right? WASM is very good for the web, right? It solves platform independence, and it has managed to get through the web standards process. So just in itself an amazing accomplishment. However, if you want something where you just want to sandbox things at a low level and you really want compatibility, performance, security, and simplicity, right? Low-level sandboxing, doing low-level rewrites close to the metal, really has a lot of advantages. So we've done this. I was at RISC-V Summit, talking to another friend from the LLVM community, and he's like, dude, you should talk to Nathan. Nathan is here. He's got this problem. He's trying to do this thing. So I was like, Nathan. And Nathan's like, yeah, we've got this codex. And they're like, process sandboxing is really hurting our performance. We're trying to do this thing with WebAssembly for better part of a year. And I'm like, no, dude, don't do that. I've been doing it for the last 3 years. It super sucks. It's not going to go well. So Android is really interested in this because half of the Android open source project is unsafe third-party code. We're like, hey, try this thing. So Nathan's like, hey, I've got this decoder thing I worked on. Why don't you guys sandbox this? And we came back 2 weeks later and we're like, here, we sandboxed the thing. It was David, and it was 4%. He's like, awesome. So we started working with the Android guys. And I think we've been kind of developing this vision of LFI. And again, LFI is this low-level isolation technology where, again, performance, we're developing it so we can fully exploit the architecture and compiler optimizations. Again, we're not LFI is not a format. Right? Tomorrow, when we figure out how to make it faster, what the compiler spits out will change. It does provide us, a really good compatibility, and so we can work with a Linux API. We can be ABI compatible. We can work with our existing tool chains. Right? I think we can build something that basically looks like a normal library, but is isolated. Again, because we're at this low level, it's much easier to do security. We can actually take the output from the compiler. We can verify it, and then somebody went even and verified our verifier against the ARM spec with an SMT solver. So if you want a verified verifier, we can help you. And then finally, again, it's this, a library is a library. You can try to kind of get very, very kind of asymptotically close to that normal developer experience. So again, I don't see this as a kind of the answer for memory safety, but I think it's kind of another tool in our toolbox, along with things like F-bound safety and these other kind of great capabilities that LLVM provides. And we're hoping this will really be something that can benefit developers. We have this slated to roll out in Android in 2026, and we're working on getting this to other parts of Google. And I'm going to actually hand it over to Zach to talk about how it works.
All right, thanks, Tal. Yeah, so now I'm going to talk about some of the more technical details of LFI. So first, what the overall compiler architecture looks like. So we basically have a new target for a sub-architecture of AArch64. We also have some support. We have support for x86, but I'll talk for the most part here about the AArch64 version. So it's a sub-architecture of AArch64, and essentially what happens is there are some patterned rewrites that happen at the very end of the pipeline, basically in the assembler at the MC-inst level. We're going to do some expansions to basically make the instructions that get generated conform to a safe subset of the architecture. And this is nice because it can handle things like handwritten assembly, inline assembly, as well as whatever gets generated from the IR. And other than just reserving a few registers, we just need to add this rewrite stage in. And once you compile for the AArch64 LFI target, you get an ELF binary out, which has been rewritten, and you can run a static analysis verifier tool to make sure all the instructions conform to the LFI subset of the architecture, and then that binary is going to be run inside of a certain LFI runtime that's going to load the sandbox and load the ELF binary into there. So the execution environment, once it's been loaded, looks kind of like this. We have a 4 GB region of the virtual address space that's going to be given to the sandbox. So that's going to be the untrusted code can access within that subset of the virtual address space and nowhere else. And that's divided into a code segment and a data segment. So the code is going to be not writable. The data is going to be not executable. And other than that, it's essentially like a normal program. And the way that we're going to restrict accesses is using this idea of, well, if we store the base somewhere in a register, then we're going to make sure all of the loads and stores are going to be expressed as a 32-bit offset from that base, which can be up to 4 gigabytes away. So let me give you an example of that. And this is now what a rewrite looks like. So this is going to happen ahead of time in the compiler. We're going to get, the normal ARH64 backend is going to generate some instructions, for example, that use like just a normal load instruction targeting an arbitrary register, and that's a 64-bit value. So it could be anywhere in the address space. Not necessarily, this is not a safe instruction for our LFI subset. So the first stage is the compiler is going to have a reserved register, x27, for example, which is going to store the base of the sandbox. And so now our rewriter, when we're compiling, is going to rewrite this unsafe instruction into a safe equivalent, where now it's expressed as a 32-bit offset from our base register using the 32-bit plus 64-bit addressing mode that ARM provides. Some instructions don't have this addressing mode, so like a load pair, for example, doesn't have this. And so we need to, instead, to handle this case, introduce an additional instruction. And in fact, also an additional reserved register. So we're also going to reserve x28, which is going to have some invariant that it always must contain a valid sandbox address, some valid address within the 4 gigabyte region. And now we can load a value into it using our sort of 32-bit plus 64-bit masking instruction. And then a load from x28 is always guaranteed to be safe because x28 always has a value within the sandbox. Right, so actually I'll talk a little bit more about the control flow in the next slide. So when we do indirect branches, we have a similar problem. Like this is sort of in some ways a memory access. And so we're going to do a similar mask to keep the instruction, keep the target inside the sandbox. And one thing that's nice about ARM in particular is since every instruction is fixed width, we just need to guarantee that each instruction individually is safe to guarantee that the overall program is safe and upholds our sandbox guarantees. And that's because, right, you can't jump into the middle of an instruction on ARM. The hardware will trap if you try to do that because of the fixed width encoding. There's also for handling system call or other system instructions. So we have some rewrites. Basically, there's like a very, a specific way of exiting the sandbox that uses a function entry point stored in a specific read-only page. And so we rewrite system call instructions to instead perform like a load from that page and then a branch to branch out into some runtime external code that can handle that system call on behalf of the sandbox. And similar thing, for thread local storage, we're not going to clobber the actual host thread local storage. We're going to use a reserved register or maybe exit in the form of a runtime call. And so talking about the runtime, this is some trusted code outside of the sandbox that's going to handle the system calls. So we have it implementing sort of a subset of the Linux API. For a lot of the libraries we want a sandbox, there are not that many system calls that get used, like decoders and stuff like that. They just need to allocate some memory and have some buffers. And so sticking to a subset of the Linux API keeps this simple and keeps it compatible with legacy code. So just as an example of sort of what this looks like when you put it all together, you get your software, you compile for the special target, and then you run it. You can run it at the command line with this LFI run tool, or in practice for a library, you'd have some, you link into your application, something that's going to load the sandbox and run it. So I have a few slides about x86 support, just to give an idea of what we have to do there. So the main challenge on x86 is we have variable with instructions, so you can jump into the middle of an instruction. And so one approach to prevent that is to use what's called bundling. So we're going to force every instruction to be part of a 32-byte bundle. And if the instruction were to span a bundle boundary, we're going to pad with some no-ops to move that instruction to the next bundle. And then just before every indirect branch, we're going to zero out the bottom 5 bits, for example, if it's 32-byte chunks or bundles, zero out the bottom 5 bits to ensure that the indirect branch must always go to the beginning of a bundle. For loads and stores on x86, we don't have this 32-bit plus 64-bit addressing mode that exists on ARM. But what we do have, you can sort of get away with that in the form of using the GS segment register. So this is actually a really nice optimization and makes the load and store sandboxing on x86 much more performant, where we can just stick the GS segment prefix on memory accesses and then swap the register to the 32-bit version rather than the 64-bit version. And this is much more performant than what you may have to do if you have a separate instruction and you can't use GS. you'd have to do like a separate move to zero out the top 32 bits of your target address register. So this is called the segue optimization. So that's sort of the overview of the two there are the two main differences between the AR64 version and the x86 version. I'll now go through some performance numbers and some of our benchmarking and evaluation. So on spec, we ran a number of benchmarks and in a number of different configurations. So we've got full sandboxing. This is just your proper sandbox. And then you can also have a stores only mode where you don't sandbox the loads. You allow your sandbox your untrusted program to read outside of the 4 GB region, but it can't store, it can't write or corrupt outer memory. And so in some cases, maybe this is okay for your threat model. And then just for sort of to break down the components of the performance, we also have a version with jumps. So this doesn't sandbox the loads or the stores. And maybe this is practical when used in combination with the hardware memory isolation mechanism like MPK on x86 or PoE on ARM. And so the x86 version, we actually have similar performance for the full sandbox, but once you go down to stores and jumps, it's not quite as good as the ARM version, and that's because you hit this floor of the control flow isolation being a much bigger problem on x86, having to do that bundling and having to not being able to use return instructions. We're still working on maybe some optimizations to make this faster, but this is sort of what the performance looks like currently. Now, for Android in particular, we're interested in using this for audio decoders and other sorts of media decoding. So we have some more targeted benchmarks for example, Opus, the Opus audio decoder, and then also for sandboxing David. David is really like so it's an AV1 decoder, and it's really a stress test for LFI because it has so much handwritten assembly in it. And so I think LFI is really sort of unique in its ability to do in-process isolation of these media decoders that have lots of handwritten assembly in them, and do it with relatively little performance overhead, roughly like around 5%. Here's a micro benchmark for the function invocation overhead. So one of the main benefits when you bring your sandbox in process is now you don't have to pay a context switch cost when you transition into the sandbox, into the untrusted domain, because you don't have a separate process anymore. And so we can get these sandbox domain switches much faster, on the order of tens of cycles rather than tens of thousands. So here I'll just have some additional ongoing work that I'll mention. This is really interesting to be applied to existing forms of in-process isolation that use JITs. So in a browser, you've got a JIT engine that's going to be compiling your JavaScript, and your compiler is trusted in this case. But if we can modify the JIT compiler so that it generates code that conforms to this LFI subset, and then have a verifier that's dynamically running to make sure that all code that gets generated actually passes verification, then we can really reduce the trusted code base by bringing the actual compiler logic outside of the trusted code base and just relying on the verifier to make sure that whatever the compiler is generating conforms to this subset. And the verifier, in fact, is quite simple, right? Because it's just verifying that every instruction conforms to the subset. So way less complicated than an optimizing JIT compiler. Another case where this is interesting is in the kernel, because your programs there are a lot more restricted, and you can't use separate processes. For example, if you want to isolate device drivers, and so LFI we're sort of investigating that as a solution for reducing the amount of privilege escalation that comes from third-party device drivers. So that brings me to the conclusion. We have an RFC online. We're interested in hearing your advice, questions, comments, concerns. So if this sounds cool to you, please come chat with us. If you're interested in using it, let us know. Thanks.
If you have questions, we have a mic on the right side, and I can also walk around if you just raise your hand.
Hi, nice work. So I probably missed this. Who is going to specify the granularity of isolation? Like the user should annotate the code? How are you going to sandbox?
So there's no annotation or anything. It's just when you compile your code, you compile for this target triple, and the machine code that gets compiled is going to have these rewrites applied to enforce that the machine code that comes out is within this secure subset, in the sense of the only instructions that get generated are ones that can access that are restricted to the 4 GB region.
So an application is going to be sandboxed. Oh, I thought like you're going to partition the application into
So we
multiple.
do it at the library boundary.
Oh, at the library
But
boundary.
yeah,
So that's what I'm going to ask. I see.
I mean, you could certainly do something with annotations if you wanted to like partition your application like manually or even automatically, but like libraries are just kind of this natural boundary, especially again, like, parsers, decoders, compression libraries are usually this very clean interface where you just, kind
So every library gets its own sandbox.
whatever library you choose gets its own sandbox. Yeah.
Oh, we can choose that.
Yeah. We don't automatically just sandbox all your libraries. I mean, I guess you could, but
Yeah, so to start, you pick one library, for example, that you want to have in the sandbox, and you're going to, modify your application to do that. And then maybe you'll put more and more in the sandbox as you, decide.
Okay.
Or you can have multiple sandboxes as well.
Okay, we can chat later, but thanks. Yeah.
So if you malloc something, does the runtime is it allocated in the 4 gigabyte address space, and then the runtime just gives you like the offset into it?
Yeah, so there's basically two allocators now. Or when you're using it from the host application, you have your normal host malloc, which could allocate anywhere, but there's also, you can call the sandbox's malloc, and that'll give you a buffer that's in the sandbox. And so if you need to give the sandbox some data, or you need to allocate a buffer where it can put its results, you allocate with the sandbox's allocator.
Yeah, thanks for the talk. It was pretty interesting. I'm actually a little curious. The registers you guys were using as part of the sandbox, are you using X25 through X28 as your sort of reserved registers? Is that restriction only on the sandbox library? Is the process itself also restricted in those reserved registers?
Yeah, so that's only in the sandboxed environment.
Okay.
Your host code is compiled natively without those reserved registers, but on the transition, part of the additional overhead in the transition time is modifying or saving or storing those registers or putting the correct values into those registers.
Okay, so I guess the big risk, so the follow-up would be, so the big risk is those reserved registers can't be put on the stack realistically, right? If you're worried about corruption or anything like that.
Yeah, so basically those reserved registers, like the sandbox base register, can never be modified by any instruction in the sandbox's code.
Okay.
So that's one of the things the verifier is going to enforce, that there's no instructions that modify X27.
Got it. Cool. Thank you.
Very minor technical question. You always showed the base being at the bottom of the region. Would there be any architectures where you only have a signed 32-bit offset, so it needs to be in the middle?
I haven't come across that, but we've only looked into ARM64 x86 and RISC-V. Maybe there are some strange architectures where this would be
Convenient.
Any other questions?
So for this to be secure, I guess do you have to like have two copies of, say, like the C library, like in a process, like the secure one and the insecure
So
one?
essentially, inside of the sandbox, everything, all dependencies of your library or whatever you're putting in there has been compiled for the LFI target and statically linked. So that includes libc. So you don't really need a different libc like source code, but you do need to recompile it for the LFI target.
Did you run, out of curiosity, any inter-ready problems? Because most C libraries assume like they're the only one.
Well, yeah. So because we have we rewrite all the system calls and the TLS accesses as well. Basically, the libc inside the sandbox has no idea about the external libc, and the external libc also has no idea. It just looks like a memory mapped region to it. So they don't actually interfere at all. And then the runtime is going to handle these system calls that come out of the sandbox libc. So they're not actually sharing any of the same system state, because all that system state for TLS or things like that gets virtualized by the runtime.
are you talking about like linking?
Also, so there's no like symbol clashes or anything like that.
No.
No, for example, you compile your library as a static blob, and then it's going to be dynamically loaded. And so that's
All the symbols are
all the symbols are private.
Like the only thing you expose are like kind of the trampolines, the interfaces like for the library that you're sandboxing.
Okay, thanks.
Yeah, I think that's all the questions. If you have any other questions, you can talk to the Zach or Tal outside. Our next speaker. Yeah.
Thanks.